Hey everyone, welcome back. Today we're going to explore something super important, designing production AI systems and how they're built to work reliably in the real world. If you've ever wondered how AI models like Claude go from just text generators to full-fledged systems powering real applications, this lecture is for you. Here's what we'll cover today. What exactly a production AI system is, its high-level architecture, user interface and API layers, orchestration and workflow management, foundation models like Claude, prompt engineering for consistent outputs, retrieval-augmented generation for real data grounding, tools and AI agents, the data layer and storage strategies, security, monitoring, and reliability, multi-tenant architecture, the request lifecycle, and best practices for production-ready AI. By the end of this lecture, you'll see exactly how all these pieces fit together to create robust, scalable, and secure AI systems. So, let's get started. Introduction to Production AI Systems. A production AI system is much more than a language model. It is a multi-layer architecture designed to handle user interactions, coordinate retrieval and tool usage, and ensure reliability, security, and observability from day one. These systems include an application layer, an orchestration layer, a model layer, and a data layer, all working together to deliver robust AI services. Production AI systems are built for scalability, security, and accuracy. Monitoring, logging, and cost control are integral, not afterthoughts. High-level architecture. The architecture of a production AI system is layered for clear responsibility. The front end captures user input and displays responses. The API gateway handles request routing and access control. The application layer orchestrates business logic. Bedrock Claude performs model inference. The data layer provides persistent storage and vector retrieval for knowledge grounding. Each layer has a single, well-defined role, making the system maintainable and scalable. User interface and API layers. The user interface layer is the entry point for interactions. It captures natural language input, streams AI responses, handles errors gracefully, and collects user feedback when needed. The API layer sits between the front end and back end. It manages authentication via Cognito, routes requests, applies throttling, and enforces usage limits. This ensures only valid and authorized requests reach the orchestration and model layers. Orchestration layer. The orchestration layer is the brain of the system. It constructs prompts by combining system instructions, user context, and retrieved knowledge. It decides which tools to invoke, calls the foundation model, formats the response, and handles retries or fallback paths if errors occur. Most of the AI application logic resides here, ensuring consistent and accurate responses. Foundation model layer. The foundation model layer is where inference happens. The system calls Bedrock runtime with structured prompts. Claude performs reasoning, summarization, classification, or generation depending on the task. Responses are returned in structured formats and passed back to the orchestration layer. Bedrock manages infrastructure, so developers do not need to provision GPUs or manage servers. Prompt engineering. A well-structured prompt includes system instructions, retrieved context, user query, and output format. Guardrails prevent unsafe or off-topic responses. Consistent prompt design ensures high quality and predictable outputs. Retrieval-augmented generation, RAG, connects the model to real data. User queries are converted into embeddings to search a vector store for relevant documents. These documents provide context for Claude before generating a response. This reduces hallucinations and ensures that AI responses are authoritative over enterprise-specific knowledge. Knowledge-based design. In this section, we discuss how a knowledge base is designed for a production AI system. A knowledge base is the indexed data store that powers retrieval in a RAG-based architecture. Documents are split into smaller parts called chunks. Chunking is a critical step because the chunk size determines the balance between context richness and retrieval precision. If chunks are too large, they may include unnecessary information. If they are too small, they may lose important context. Each chunk is converted into embeddings and stored in a vector store. Along with embeddings, metadata such as source, date, and tenant ID is also stored. This metadata allows filtering of results and ensures that users only retrieve documents they are authorized to access. Tools and AI agents. In this section, we explore how tools and AI agents extend the capabilities of a language model. A language model alone can generate text, but it cannot perform actions without external tools. The model decides which tool to use based on the user's intent. An agent controller then executes the selected tool, such as making a database query, calling an API, performing a search, or triggering a workflow. Once the tool completes its task, the result is returned to the model and included in its context. The model then generates a response using this updated information. This enables automated, multi-step AI-driven processes. Data layer. The data layer provides persistent storage for all components of the system. It stores both structured and unstructured data, along with system-related information. PostgreSQL, typically through RDS, is used to store structured data such as user records, application data, and conversation history. S3 is used to store raw documents, uploaded files, and artifacts. The vector database stores embeddings used for retrieval. Prompt templates and system logs are also stored in the data layer, allowing auditability and continuous improvement. Security and governance. Security operates at multiple levels in a production AI system. Authentication is handled by services like Cognito, which verify users and issue tokens. IAM policies control access to services and models, ensuring only authorized actions are allowed. Prompt guardrails are used to prevent misuse, either through system prompts or external enforcement. Tenant isolation ensures that users can only access their own data. All API activity is logged for auditing and compliance purposes. Monitoring and observability are essential for maintaining a production system. Metrics are collected to track system performance and health. Latency metrics help identify delays in the system. Token usage is tracked to monitor cost. Error rates are monitored to detect failures. CloudWatch collects metrics from system components and provides dashboards for real-time visibility. This helps teams detect and resolve issues quickly. Cost management is important in AI systems, especially at scale. Each AI request includes multiple cost components. Token usage is billed based on model usage. Retrieval operations and database queries also add cost. Compute resources such as Lambda execution contribute as well. To reduce cost, prompts should be optimized to remove unnecessary content. Caching can also be used to return stored responses for repeated queries. Reliability ensures that the system handles failures properly. Failures such as API errors or throttling can occur in production systems. Retry mechanisms with exponential backoff are used to handle temporary failures. Response validation ensures that outputs match the expected format. If validation fails, a fallback prompt is used. If all retries fail, the system returns a safe degraded response instead of an error. In a multi-tenant system, multiple users share the same infrastructure while keeping their data isolated. The tenant ID is extracted during authentication and passed through all system components. Retrieval queries include tenant-based filtering to ensure data isolation. Prompt construction may include tenant-specific instructions. Tenant isolation must be enforced strictly to prevent data leakage. Every request follows a fixed lifecycle in a production AI system. The process starts when a user sends a request. The system first authenticates the user. Then, it performs retrieval to gather relevant information. After that, a prompt is created using the retrieved data. The model is invoked with the prompt to generate a response. The response is then validated before being returned to the user. Finally, the entire request and response are logged for auditing and debugging. Reference architecture. The reference architecture shows how system components work together. The front end is hosted using Amplify. API Gateway provides the entry point and handles access control. Lambda performs orchestration of the workflow. The model is accessed through Bedrock for inference. PG Vector on RDS stores both relational data and embeddings. S3 stores documents. CloudWatch monitors all components. This architecture is serverless, scalable, and production-ready. Common AI architecture mistakes. There are several common mistakes in AI system design. Hard-coded prompts make updates difficult. Lack of monitoring prevents visibility into system performance. Poor chunking reduces retrieval quality. Missing tenant isolation creates security risks. Lack of response validation allows incorrect outputs to reach users. Avoiding these mistakes improves system reliability. Final design principles. A well-designed production AI system follows key principles. Scalability ensures the system can grow without major changes. Observability ensures visibility through metrics and logs. Security ensures proper authentication, isolation, and guardrails. Grounding connects the model to real data through retrieval. Cost control ensures efficient use of resources. Following these principles results in a reliable and production-ready AI system. Thank you.